Welcome to this section of the course where we're going to talk about trig identities. And in the largest sense, trig identities are basically formulas or relations that you can write down that kind of relate some of the trig functions to other trig functions. For instance, we've been talking about the little rainbow that we would draw on the board that would tell us how to write secant in terms of some other trig function, or cotangent, for instance, in terms of a tangent function. That was the simplest form of what we call a trig identity. And really the main thing that they're used for is to let you simplify expressions. So you kind of put those identities in your toolbox, your mathematical toolbox, and you just pull them out to be able to use them whenever it helps you to simplify a problem. So let's go ahead and talk a little bit about identities. We're not going to cover all of the trig identities by any stretch of the imagination. There are literally hundreds of them. But what we can do is kind of talk generalities. So if you recall, we wrote sine, cosine, tangent, cotangent, secant, and cosecant. And we wrote those down, and I taught you that if you kind of draw a little rainbow here, you'll be able to write, for instance, cotangent as 1 over tangent, secant as 1 over cosine, etc. And those are actually trig identities. So let's go ahead and write them down, and we'll use them here in a minute to do some simplification. So for instance, cotangent was equal to 1 over tangent. That was one of them we wrote down. Secant was 1 over cosine. That was another one we wrote down. And cosecant was 1 over sine. And we wrote that down. Okay? So these are identities. What it's telling me is I can write a cotangent in terms of some expression of a tangent. It just so happens it's fairly simple. It's just 1 over tangent. Here I can write a secant in terms of a cosine and a cosecant in terms of a sine. I've given you this nice tool to help you remember these here. Let's go ahead and talk about one of the most powerful trig identities around. Actually, it's one of the only ones that I have committed to memory. And that's the following. This is another trig identity. What it means is sine squared of theta plus cosine squared of theta is equal to 1. This is very, very important, and you'll see it all over the place, and you'll use it a lot too. First, let me explain what do I mean by this term sine squared of theta. For instance, what this would mean is if you take the sine of some angle theta, and then whatever that number turns out to be, you square it. That's what it means when you say sine squared of theta. You're not squaring the theta. What you're doing is you're operating on the theta, and you're taking the sine of it, and then whatever this number happens to be, then you square it. Let me briefly explain where this identity comes from, and I think it'll be kind of enlightening. Remember the unit circle that we had? We've been talking about that all day, really. You have a unit circle, it's radius 1. Okay, that's why it's called a unit circle. And we normally draw it kind of like this. My circle's not perfect, but you see what the main point is. It's a circle, it's a radius 1, okay? If you pick some random angle here, like this angle would be, let's call it theta. That's, after all, what we've been talking about. And then if we want to find the sine and the cosine of this guy, we had been talking about is you take the projection down here, like this. And then what we've been really saying, really in the entire class, is this measure right here is called the sine of theta. That's by definition what the sine of theta is. And then this right here is called the cosine of theta. And of course that leads to what we had been talking about before, which is that sine has to do with the y component of some projection. In this case, the projection of this line on the y-axis, really. And the cosine is the projection of this line on the x-axis. Okay, so that's why I have sine and cosine. Now, remember the Pythagorean theorem. Pythagorean theorem, which is something that you probably have seen before, and I think we've even used it before. And that's basically that c squared is equal to a squared plus b squared. This is something that's just given in geometry or in sort of basic geometry of triangles. And that says that the hypotenuse, which is the the longest length in a triangle like this, if this is a right triangle, this is the hypotenuse, it's the longest side, it's opposite the 90-degree angle, and then here's one side and here's the other side. A and B really don't much matter, they're just added together, but C has to be the hypotenuse, okay? This is always true of every right triangle. The hypotenuse squared, this length squared, is equal to this length squared plus this length squared, okay? But look at what we have here. We actually have a right triangle right here in front of us, okay? The hypotenuse happens to be this length right here, but notice that this is a unit circle, so the hypotenuse always has a length 1. No matter where you rotate your angle in this diagram here, it's a unit circle, so by definition the hypotenuse is always going to be 1. Okay? So, if the hypotenuse is always 1, I could put 1 squared here for C, but 1 squared we all know is 1, so I could just put a 1 here. Okay? And then I would need to figure out, well, what are A and B? Well, we said A and B are the other lengths of the right triangle. Here's one length, and here's the other length. So if A is this one, that would be cosine squared, and then the other one would just be sine squared. So you see what we've done is we've arrived at this identity right here. This identity comes directly from the unit circle, knowing that it's a unit length on the hypotenuse, and knowing that the other sides of the triangle are sines and cosines, and so that's how you get that. That's where that identity comes from. I'm not going to give an explanation for all of the identities because honestly it would take forever, and many of them are derived using calculus anyway, and so we're not there yet. But this is an important identity. Another identity that we'll use and that's important is 1 plus tangent squared of theta is equal to secant squared of theta. And again, I'm not going to tell you where this comes from. I'm just going to tell you that if you have tangent of some angle and you take the tangent of it and you square it and you add 1 to it, what you're going to get is the secant squared of that same angle. And finally, if I have 1 plus cotangent squared, that's going to equal cosecant squared. Again, we have thetas everywhere here. So if I have the cotangent of an angle and I take the cotangent and then I square it, then I add 1 to it, I'm going to get the cosecant squared. And we're not, as I mentioned a minute ago, we're not going to cover all of the identities in trig. If you open any trig book up, you will find entire chapters on identities, and literally you can pull books off the shelf that will have hundreds and hundreds of these what we call trig identities, which just say that you can write this in terms of this, okay? And you can go on and on and on. What I'm going to do is show you some of the basic ones and show you kind of how you start to prove some of these identities and work some problems using these identities, and hopefully you'll be able to apply some of those techniques to problems involving different identities that we're not going to cover in this class. So let's leave this on the board. We have quite a few of them up here. We'll draw a line like this, okay? And let's work a problem. Let's say the problem is that they want you to verify a certain identity, and the problem is going to go like this. Let's say you have cosine theta times secant theta equals 1. You're going to see problems like this popping up all over the place in trig and pre-cal, and basically what they're going to ask you to do is they're going to give you what they claim to be an identity. They're going to give you what they claim to be an identity, and they're going to tell you, prove it to me. And what you're supposed to do is you're supposed to use all of the tools in your toolbox, all of these other identities that are given you in the book, and use them to prove that this is true. And so we're going to do some examples, and I think you'll see how to do that. The first thing I notice is this secant here. I can write this secant in terms of a cosine. So let's try to do that. Cosine theta, all I've done is copy this down again, times secant theta. But secant theta is given by 1 over cosine theta. And I'm asking myself, is this equal to 1? Because I'm trying to prove that this identity is true. Of course, when I do this, I will see that I'll have cosine theta over cosine theta, which does equal 1. So what I have in the end is 1 equals 1. And the answer is yes, this does check out. So this initial thing I started with is in fact true. The reason I know it's true is because I use one of my identities to plug it in, manipulate the left-hand side of the equation and reduce it to prove to myself that the left-hand side of the equation was in fact equal to 1, which is what the initial problem told me that it should have been equal to, which is 1. And some of the equations are going to have some mess on the left-hand side and some mess on the right-hand side. Your goal is to beat either side or both into shape so that you prove that they're equal to each other. Once you've gotten to that point, you're done. You don't have to keep going anymore. Okay? So that was a fairly simple problem. We just used one of our identities to prove that that expression was true. What if I have sine theta times secant theta equals tangent theta? Now, also I want to point out, when I have something written like this, you can always assume like an implied parentheses around this stuff. This sine of this theta is completely separate from the secant of this theta, and these two quantities are multiplied together, multiplied by one another. So don't start trying to take the sine of the secant. I mean, you take one, you take the other, and you multiply together. Okay? My advice to you is, if you don't know how to get started, do something. Pick something and simplify it and see if it helps you get any closer to your answer. So when I look at this, the first thing I notice is I know how to rewrite the secant function. I don't know if it's going to help me finish the problem, but I know how to rewrite it, so let's try to do that. So what I have on the left is sine of theta times secant of theta. Secant of theta is 1 over cosine theta, and I'm asking myself, is this equal to tangent of theta? Okay? Well, when I do this multiplication, I'm going to have sine of theta over cosine of theta, and I'm asking myself, is this equal to tangent of theta? Well, if I remember back, and hopefully you remember this from a previous section of the class, sine over cosine is the very definition of what the tangent function is. So what I have here is tangent theta is equal to tangent theta, which means, yes, check mark, it is correct. Which means this initial thing I started with is in fact true. Sine times secant does equal tangent. And this is how you would write it down in your test. You'd plug in 1, you'd simplify, and then at the very end you want to have an equality with the same thing on each side. And then you've proven to yourself, to the teacher, to anyone else, that that identity is true. What if you had 1 plus cosine of theta times 1 minus cosine of theta? And I'm asking myself, is this equal to sine, with a question mark, sine squared theta? Well, notice I have cosines, and sines, and there's not much more to really simplify here as far as using any of these things up here. Certainly nothing looks directly like any of these identities. I can't really substitute anything right away. I could substitute over here for sine, but then it's not going to look really right. I think the most direct thing to do here is to go ahead and expand this out using FOIL. Expand this out. So let's do that. First terms times the first term. 1 times 1 gives me 1. Again, I'm just using FOIL. And for those of you that may not remember, I'm going to multiply the first, the outside, the inside, and then the last terms. I'm going to add them all up. That's how you multiply terms like this. The outside term times the outside term is 1 times a negative cosine theta, which is just going to give me a negative cosine theta. The inside terms is 1 times cosine theta, so I've got a plus cosine theta here. And then the outside terms is a positive cosine theta times a negative cosine theta, which gives me a negative, because negative times positive is negative, cosine squared theta, because cosine times cosine gives me cosine squared. Negative sign comes from the signs here. And I'm asking myself, is this equal to sine squared theta? Okay. Well, pretty quickly you can figure out that this is going to look a little nice, because this term cancels with this term, this negative cosine theta. It adds with that cosine theta and gives you 0. So what I'm left with here on the left is 1 minus cosine squared theta equal to sine squared theta. Okay? Well, now, this is starting to look a little bit like this identity up here. If I take this identity, okay, and I solve for sine squared, then all I do is I subtract cosine squared from both sides. So it'll have sine squared is equal to 1 minus cosine squared. Okay? So I've just proven myself that 1 minus cosine squared is sine squared. And just to show you that, what I'm saying here is sine squared is equal to 1 minus cosine squared. All I did was subtract the cosine squared from both sides, and that equality is true. So, knowing that, 1 minus cosine squared I have here and I have here, so I'm going to say that's equal to sine squared of theta, which on the right-hand side, of course, is equal to sine squared theta from before. So yes, this checks out. Again, the last answer should have the same thing on both sides, and that proves to you, yes, they are equal. And I just got to this point and used this identity to show me that it's true. Without these identities up here, you really can't press any farther. That's why they're useful. That's why they're very useful. And this technique is going to apply to identities in general. You're trying to simplify identities or simplify expressions. What if you had sine of theta over cosecant of theta plus cosine of theta over secant of theta? And I'm asking myself, is that equal to 1? Okay, and I'm asking myself, is that equal to 1? Well, the first thing I need to really do is look at what I have here. I've got a sine, a cosine. I can't really do much to simplify that. But I do have a secant and a cosecant, and I can do my best to try to simplify that. So let's use our identities from up here. We'll keep the sine on the top. Cosecant is over here, given by 1 over sine. So that's 1 over sine of theta. I just substituted in for cosecant here. And I say, okay, I'm going to add to that this next term, which is cosine of theta over secant, which is given here, which is 1 over cosine of theta. Okay? And I'm going to ask myself, is this equal to 1? Okay, is this equal to 1? And so what you need to do is simplify your fractions here. And if you remember, when you divide fractions, you take the bottom and kind of flip it over and multiply times the top. So what you're going to have here is sine squared theta plus cosine squared theta equals 1. That's going to be the answer to the question, because when you're dividing these two things by each other, you're going to take the bottom, flip it over, so you have the sine times the sine on the top is going to give you sine squared. Now this, you can stop exactly right here, because what you've done is you've started at this point, you've ended at this point, and what you've arrived at is something that you know to be true. So you know that this identity is true. So, either you need to end up with things on each side of the equal sign to be true, or you need to end up proving that you've ended up back at one of these inequalities. What if you have secant theta minus cosine theta equals tangent theta times sine of theta? And the question there is that identity true? I want to try to use these other identities to prove that this is true. Okay. Again, I've got a cosine, a tangent, and a sine. The best I can probably do is try to substitute for some of these things. So for secant, I'm going to substitute in here and say this is equal to 1 over cosine of theta. And this is, of course, subtracting off the cosine of theta here. So on the left-hand side, all I did was substitute for secant. On the right-hand side, I know that tangent is equal to sine of theta over cosine of theta. I know that that's true, so I plug it in there. And I just multiply by the good old sine theta that's already left here on the right-hand side. So what I'm going to do here in the next step is I'm going to multiply both sides of this equation by cosine theta. The motivation here, and this is where working a lot of problems becomes handy, because this may not seem obvious at first. The motivation here is I don't like this fraction, even though I created it in the first place. I don't like this fraction with cosine theta, and I don't like this cosine theta over here. So what I'm going to do to help myself here is I'm going to multiply this whole equation, both sides, by cosine of theta. I can do that. Remember, I can do anything I want to both sides of an equation. No problem. So cosine theta times the left-hand side. Cosine theta times this term here is just going to be 1, because cosine theta over cosine theta is 1, minus cosine theta times cosine theta is cosine squared theta, okay? And then on the right-hand side, again, multiplying through by cosine theta, the only thing that's going to happen here is this cosine is going to cancel with this cosine, and I'm going to be left with sine times sine, which is just sine squared theta, okay? Okay? Now, this is starting to look a good bit like this right here, so I'm just going to move this cosine over here. I'm going to have 1 is equal to sine squared theta plus cosine squared theta. And then you're there, you're finished, because what you've done is you ended up at a place where you've basically proven that this term that you started with is equal to a known equality, a known trigonometric identity that's already proven. So then you can stop there and say, this is true, I know this is true, so therefore I know the first part is true. And my advice to you as you work these problems is just make sure that every step you do, you're confident it's legal, okay? No matter if you're going down the wrong road or the right road, as long as the step that you've just done is legal, you can always undo it. Just don't go out too far on a limb trying to do things you're not sure is legal to do. Like in this step, we knew that substituting for secant is correct. Or it's not necessarily correct, but we knew it was legal to do it. I didn't know ahead of time that that would help me, but I knew that I was allowed to do it. Multiplying both sides out by cosine, you may not think in the beginning or initially that that would definitely help you get to the solution, but you know it's legal to do, okay? But don't start doing weird things to the equation that you're not confident you're legal to actually do. And this is why I'm hoping that a course like this is useful, because working problems is really the only way you get the experience to figure out if these things are okay. What if you had secant squared theta minus 1 over secant squared of theta, and I'm going to ask myself, is that equal to sine squared of theta? Okay, is that equal to sine squared theta? Well, and again, I've had a little bit more time to think about this problem than you guys have. In fact, I have them on my paper here. I've already thought about them, so I'm going to be a little bit ahead of probably where you are. But first thing you should really look for is the fact that I have this secant squared minus 1. This starts to look a whole lot like this, because if you look over here, I think you'll be able to convince yourself that if I solve this equation for tangent squared, I'll just subtract this 1 from both sides. Tangent squared is equal to secant squared minus 1. And I'm just getting this from this identity here. This is nothing new. Solve for tangent squared. Subtract 1 from both sides. Now here I have a secant squared minus 1. So basically in the problem, when you see something obvious like this, that they've given you something that looks like it's using an identity, use it. Most of the time it's going to be the right way to go. So in the top I can just put a tangent squared here, because in fact that's what we said secant squared minus 1 is equal to. On the bottom we have a secant squared, and on the right hand side of the equal sign we have a sine squared theta. Okay? Okay, the next thing to really do is, let's go ahead and move this secant squared over here, so I can say tangent squared theta is equal to sine squared theta times secant squared theta. All I did was multiply both sides by secant squared. And then I'm going to continue simplifying the right-hand side by noting that secant is equal to 1 over cosine. So secant is equal to 1 over cosine, so since secant is equal to 1 over cosine, but I don't have secant here. I've got secant squared here. So then secant squared is 1 over cosine squared. Okay? So secant squared here is going to be equal to 1 over cosine squared theta. Okay? Now I think you might start to see where this is going, but just to be absolutely crystal clear, let's continue over here. What I have on the left is tangent squared, and what I have on the right is sine squared of theta over cosine squared theta. Now you can really stop here and say, well, sine of a cosine is tangent, so this is tangent squared equals tangent squared, that's good to go. But if you want to absolutely prove it to yourself, this is equal to sine theta over cosine theta all squared, because remember, anytime you have a fraction and everything in the fraction is raised to a power, that's equal to the numerator raised to the power divided by the denominator raised to the power. So these two steps are exactly equal. And then, of course, sine divided by cosine is tangent, and the whole thing we just said was squared, so then that's why I can write it as tangent squared theta. So once you're to this step, you've reduced both sides to tangent squared theta, and then that basically proves to you that the whole problem is a done deal, and you've proven it to yourself. So the only trick here was to notice that there was some similarity here and use this identity. And the other trick is when we multiplied by secant squared. I knew to do that because I knew in my head that secant was 1 over cosine, and I knew that if I had a cosine and a sine on the right-hand side here, that I would end up with some kind of tangent quantity, and I knew that that's where I was trying to go, and so that's why I did that. Again, this kind of thing just comes through practice. So don't feel bad if you're watching this and you're not there with me so quickly. It's going to come through practice. What if I had secant squared theta times cosecant squared theta equals secant squared theta plus cosecant squared theta? And I'm asking myself, is this true? So I'll put a question mark there. Is that quantity true? Again, just looking at this, you're like, well, where do I begin? Well, my advice to you would be, don't be afraid to roll up your sleeves and get a little bit, get your hands dirty with this. You know that secant is equal to 1 over cosine. You know that cosecant is equal to 1 over sine. And so you have the same terms over here, and so my advice to you would be to start plugging in for these things and start to figure out where they go. But the trick is to figure out, well, which identity do I use? Do I use this identity with the cosine, or do I start to use maybe this identity that involves a tangent? I can't give you a good answer there. The only thing I can tell you is you play with these problems enough and then you'll eventually get there. So what we're going to do first is we're going to use the secant squared identity here. Okay? Secant squared is equal to 1 plus tangent squared. To me, that's sort of a dead giveaway. They're giving you a problem and you have an identity that already involves secant squared, so let's use that. Secant squared is 1 plus tangent squared of theta. 1 plus tangent squared is secant squared times cosecant squared, which is, again, a dead giveaway because there's an identity that involves it right there. 1 plus cotangent squared theta. Okay? And on the right-hand side, I'm going to use the exact same identity. Secant squared is equal to 1 plus tangent squared. 1 plus tangent squared. And then cosecant squared is 1 plus cotangent squared. So plus 1 plus cotangent squared of theta. So all I did was plug in here for secant squared, 1 plus tangent squared, cosecant, 1 plus cotangent, and then the same thing on the right-hand side. This is all, of course, added together on the right-hand side. And then the next thing you need to do is just start multiplying this out in all of its glory, and then hopefully things will start canceling and reducing. And here's really the best advice I can give you. If you start to simplify something, and it doesn't look like things are canceling, or it's not obvious where to go, you may have taken a wrong turn. So you can just back up and try a different substitution or a different identity. So let's see if we get some simplification here. 1 times 1 gives me 1. The outside terms, 1 times cotangent squared is cotangent squared. Tangent squared times 1 is tangent squared. And the last terms, tangent squared times cotangent squared. Okay, all I did was write FOIL out. First term, outside, inside, last terms. And on the right, I'm just going to write this as 1 plus 1 is 2 plus tangent squared of theta plus cotangent squared theta. Okay. Now, the next thing I need to look at is what could I possibly simplify here? if you look here, I've got a cotangent squared, here I've got a cotangent squared, here I've got a tangent squared, here I've got a tangent squared. Remember, the goal is to get the two sides of the equal sign to add up. Here I've got a 1, here I've got a 2, and I've got this little leftover term here. So I'm betting that I can simplify this and arrive at the answer. So let's try that. All I'm doing is writing down the left-hand side. I've done nothing different. Now when I get to here, tangent times cotangent. Remember, cotangent is simply 1 over tangent. So cotangent squared is 1 over tangent squared. So this term right here is tangent squared times 1 over tangent squared. Cotangent is 1 over tangent, and so that's why you get this. This term, as you can see, is just equal to 1. So this term is just equal to 1. So now I've got my 1 plus 1. It's going to give me my 2 plus cotangent squared theta plus tangent squared theta. And you can see right away that now the left-hand side is exactly equal to the right-hand side. Exactly equal to the right-hand side. So I'm done. I don't need to move any farther. I mean, I could write this again down here, but it's going to be the same thing as what I have on the board. Again, sometimes it may not seem obvious the way to go. Here I just substituted using these identities and started simplifying, and it started to look like it was going to work out, so we continue moving forward. And sometimes it's not going to look like it's going to work out, and then you'll just have to stop, scratch your head, and back up and move on. Okay, got a couple more problems here. What if we have cotangent theta minus 1 over 1 minus tangent theta equals cotangent theta? And put a question mark because we're trying to prove to ourselves that this is true. Okay. What I want to try to do next is I've got a cotangent here and a cotangent here and a tangent here. So it may not seem immediately obvious what to do next, but I do know that I can write this cotangent in terms of tangent. So let's do that. Just rewriting the left-hand side of the board equals cotangent is 1 over tangent. Now, here again is where you get into your technique here, because you got to figure out, what do I do next? Do I try to plug in cotangent? Do I try to put a tangent in there? Well, those paths could lead to something, but I know that if I multiply both sides by this denominator, I will have over here some quantity, and I'm going to have some tangents canceling, because eventually when I multiply this, I'm going to have, in one of the terms, I'm going to have a tangent canceling, and anytime I can try to cancel, I'm going to do that. So let's multiply both sides by 1 minus tangent. On the left, I'm just going to get cotangent theta minus 1, because the denominator cancels. When I multiply by 1 minus tangent, it will cancel on the denominator. So I'm left with the numerator. And then I'll have 1 minus tangent times 1 over tangent. All I did was, I haven't actually multiplied yet, but I've just written it out. And so this will be cotangent minus 1 equals, what I'll have over here, if I multiply this term in, 1 over tangent times 1 is again 1 over tangent. Okay? And then this will be minus tangent over tangent, because tangent times 1 over tangent will be tangent over tangent, which is 1. So I'll have a 1 right here. Now look, things have started to look up, because I've got it almost in the same form, and on top of that I know that tangent up here is 1 over tangent is equal to cotangent, so I've really got my answer already. Cotangent theta minus 1 is equal to cotangent theta minus 1. That checks out. I'm good to go. I just used this relation here to write this in terms of a cotangent, so my identity is complete, and I'm done with that guy. We'll do one final problem in this section on trig identities and wrap things up. What if I had sine of theta plus cosine of theta over tangent squared of theta minus 1 equals question mark cosine squared theta over sine theta minus cosine theta. So this is sort of a graduate level problem here. See if we can figure out how to do this. Okay. The first thing to note is to just try to figure out what could I possibly do next. And the thing that I notice right away is I've got a tangent squared minus 1. So I'm looking for something that looks like that. Of course, this doesn't quite fit the bill. This is a tangent squared plus 1. Okay. Here I've got a cosine squared. I've got a cosine squared here. I could write it as 1 minus cosine squared. Okay. But I think the way I'm going to go here is to cross multiply. Anytime I have fractions like this, I want to just cross multiply and get rid of things. What I mean by that is you multiply both sides by this term here on the bottom, and so you'll have the right side multiplied by tangent squared minus 1, and then you'll also at the same time multiply both sides by this denominator, sine minus cosine, and so you'll be multiplying the left by that. That's called cross multiplication. You can multiply like this when you have fractions. So to do that, it'll be sine theta plus cosine theta. All I've done is written down this numerator times this denominator, sine theta minus cosine theta, equals, and I'll be multiplying these terms here, cosine squared theta times tangent squared theta minus 1. All I did was multiply those. Of course, I haven't actually done the multiplication yet. So let's do this. First term times first term is sine squared theta. The outside term, sine times negative cosine, is negative sine theta cosine theta. This term times this term. These two terms will be just positive sine theta times cosine theta. Immediately I'm starting to like this because I know these terms are going to cancel. And then the final term is going to be negative. Negative times positive gives you negative cosine squared theta. Okay? And then on the right-hand side, what I'm going to have when I multiply this out is cosine squared times tangent squared minus, this times this gives me this term, minus cosine squared times 1 is just cosine squared. Okay? Now let's go ahead and start simplifying. This is going to cancel with this. That's going to start to look pretty good. So let's go forward there. Sine squared of theta minus cosine squared of theta equals cosine squared times tangent squared, but don't forget, I know that tangent is sine over cosine, and if I write this as sine over cosine, I'll have cosine squared times sine squared over cosine squared, tangent squared is sine over cosine squared, minus this final term, cosine squared. The only reason I did that was because I just want to try to simplify things, and I want to get rid of that. Now it looks like the problem is solved. Sine of sine squared of theta minus cosine squared of theta is equal to sine squared theta minus cosine squared theta. So it checks out. And really this kind of thing just comes from practice. The cross multiplying thing you may not immediately think about. Just go ahead and do that. And it looks like it's pretty messy until you realize, well, this cancels, and then until you realize I can change this tangent into a sine over cosine, which will cancel, and that'll put it right in the right form. So I remember when I first learned this stuff, it becomes difficult because you're going to learn about a lot of trig identities, page after page after page after page. It's going to be difficult. The only thing I can tell you is keep practicing problems, keep working problems, and then as you gain experience, you'll get better and better and better at these kinds of problems.